NEP, but I hope that the agenda is a really interesting topic also in the NEP field. So I think this is helpful for you. So the motivation is I would like to prove if this very famous so-called unified scheme is really the case or not. And in the unified scheme, the type 2 and the type 1 CFOTs are assumed to be intrinsically the same, but actually this is molecular torus, which makes a difference between the two the types. And so the key question is if we really have this donut-like structure, so-called the molecular torus. And now for the advent of the ALMA enable the spatial resolved observation to start to have the spatial resolved observation of the molecular torus, but it is pretty much limited to very nearby agent like 1068. And also the midway for the interferometry start to show the sum of the structures. So all of these pieces of the information show that we do have some anisotropic distribution of materials around the active galactic nuclei, but it is still very difficult to prove what's happening inside the molecular torus. So instead of these emission observations, we are proposing, we have been carrying out this absorption observation. If we have the molecular torus, something like this, and the inner edge should be limited by the sublimation temperature of dust, which is around 1500 Kelvin. Then if we can use this continuum, this inner edge as a continuum source, then we could be able to observe the molecular torus in absorption. And if this actually the emission from the inner edge of the torus is dominant, actually the effective spatial resolution is really high. And for this type of observation, we propose to observe the CO, carbon monoxide, a fundamental low vibrational transition at 4.6 microns, which is actually the vibrational, the quantum number changes by 1, and also rotational quantum number changes also by 1. And if delta J equals +1, it is called R branch. If delta J is -1, it is called a P branch. And you can see many lines almost at the same region. And if it is summary equilibrium, you should follow this Boltzmann equation. So to observe this one, we use the Akari satellite. And one of the very big merits of the Akari is a very spurious sensitivity. So we can convey the survey type of observation of many sources. But unfortunately, the spectral resolution is not so good. So we can't resolve each the rotational transitions, but we can observe the P branch and R branch in a set. So this is the example of Akari observation of one of the URAGs called UZC 5101. And here you see the very broad feature of the CO, carbon monoxide, which is completely different for the galactic sources like this. This is, again, carbon monoxide is quite sharp. So we compile the CO absorption feature toward the URAGs using Akari in red curves and also from Spitzer. Because the carbon monoxide features are almost at the edge, a longer wavelength edge of the IRC. So if you have the redshift, they will go out from the Akari band and goes into the Spitzer band. So we made the combination fitting using the Spitzer band and also the Akari band. Also, we have some gap in between. And as I said, the Akari, the spectral resolution, spectral resolution is not so good. So we can only see the P branch and R branch features. But even from these features, we can tell the Coulomb density and also the temperature. Because especially from the width of the features, we can tell that these features are really hot components, spanning something like several hundred Kelvin, which is much higher than the ordinary temperature of the ordinary interstellar cloud material. And the Coulomb density, which corresponds the carbon monoxide Coulomb density is in the order of the 10 to the 19th or the 21st, which corresponds to the hydrogen Coulomb density of 23rd to 25th, which is really, really high. If it's ionized, it is completely comptontic. And so we have detected a very large Coulomb density of hot components. And where is it from? So if we compare, for example, our observed the Coulomb density to that of the Coulomb density observed from the X-ray observation, actually the X-ray observation seems to show the systematically larger Coulomb density. But if we compare our Coulomb density with that of the CK2 feature Coulomb density, Coulomb density, they seem to be consistent with each other. So probably the X-ray is coming from really the center of the source, and they have additional ionized components here. But we are observing most probably we are observing the molecule only, the molecular torus only, with the near infrared continuum source as the background source. So this is our interpretation. And also the Coulomb density is really high. The ordinary PDR or ultraviolet excitation is impossible to have this large number of Coulomb density of region. So we propose that this region, hot components, several hundred components, is most likely to be excited by X-ray dominated region. And also very interestingly, the Coulomb density, for example, this is the Coulomb density inferred from all of observation. CFAT1 almost none, well, consistent with the unified scheme. CFAT2 shows the absorption components with a Coulomb density distribution, something like this. But more interestingly, actually, the composite guys, including the CFAT and the starburst, has larger Coulomb densities than the pure CFAT2, which means could be the torus structure could be affected the nuclear starburst activity. So the Akari observation shows that we do have the very hot components could be going up to the 1000 Kelvin with a very large Coulomb density, and most likely due to the molecular torus. But unfortunately, we cannot make the spectroscopic resolved observation, so we go to Subaru to make the best use of the high spectral resolution. But unfortunately, the sensitivity, even with an 8-meter telescope, in M-band is very difficult to make observations. So the number of the sources which could be observed by Subaru is very much limited. So they pretty much complementary with Caliban. So this is observed spectrum. One of the observed spectrum, U log 08572 plus 3915. So you can see very beautifully. This is a band center, and this is R branch. P branch. This is R branch. So you can see many lines. The rotational transitions are pretty well resolved, and going up to something like a 19, Jacob 19 or 20. So we do have many lines. By the way, these are the atmospheric absorption features. So, and also very interestingly, we have several velocity components. So this is J-core 0, J-core 1, J-core 8, J-core 20, J-core 16. And for example, we have this is the difference between the observed velocity and the systemic velocity. And we do have the systemic velocity components, but this will disappear at the high J level. So which means that this component is a really cold component. So most probably this is due to the host galaxy. But we do have other components like outflow components with a velocity of 160 kilometers per second, which is persistent up to the very high J. And also we do have some components like 100 kilometers per second inflow component, which can be seen only at very high J, which means very hot component. So we make the composition of the components. This is a J-core 4, this is J-core 12. And for 5 components, and I'm not going into details, but for example, if you take one of the components, component C, this is what we call the population diagram, which shows the Coulomb density normalized by the degeneracy as a function of the temperature or excitation temperature. And if it is linear, which means the thermal equilibrium, and it is pretty much close to the linear, which means the thermal equilibrium, and the slope shows the temperature, roughly something like 700 Kelvin, which is really high. And if it is the thermal equilibrium up to J-core, well, 2000 Kelvin region or something like that, which means we should have the very high density, like 10 to the 7th per cubic centimeters. So we are really observing the very hot and also the dense components. And so assuming that if it is hydrostatically supported this structure, then we should actually the velocity width we observe should be related to the rotational velocity and also the height of the structure. Then if we assume this equation that actually the velocity width should be proportional to the inverse square root of the distance from the center. Then our interpretation is that we have 2 outflow components, which should be pretty close to the central region. And we have one inflow component, although this component is very high temperature, but it has a very narrow line with this, which could imply that probably this component is far away. So most probably this is a cartoon picture of our understanding of our observation that we are seeing the outflow component with a very high temperature, but another component which shows the inflow component a little bit far away from the center. So but this is completely different. For example, as a type of the observation, this is the similar observation toward NGC 253 starburst galaxies, and you can see pretty quickly that the absorption disappears at the very high. Only you can see it very low J, which means the temperature is really low, something like a 30 Kelvin. So which is consistent with the ordinary interstellar medium is being seen in absorption. But another puzzling stuff is, for example, if you look at the bulk cluster, Mercurian 231, we have a very beautiful, completely flat spectrum, which shows no hint of the CO absorption. So this is really puzzling. This is a bulk cluster, so the huge absorption in optical, but almost no absorption in CO. So the puzzling thing is Herschel made the emission observation of the pure rotational transition up to very high J. So then this shows the so-called SLED, spectrum line energy distribution. And both the Mercurian 231 and LGC 253 shows a similar distribution up to the very high J in emission and among the other ULOGs. But they are completely different in absorption. Only ULOGs shows the high J in absorption, but they're not starburst and not the Mercurian 231. So we are looking at a very good hint of the geometry, which cannot be traced by in emission. So the absorption is really complementary with the emission observations. So as I said, that we are seeing the components of the high temperature with a large Coulomb density, something like a 10 to the 23rd, with several velocity components. And also another point is the covering factor, large covering factor. Actually, the observation depth is very deep. So the covering factor is as high as 8.6. So this is not the random distribution of material. We should have the very systematic structure to make this very deep absorption. And another puzzling is not every CFAT 2 shows this the absorption. So actually, the number of the sources which we could really observe is very much limited. So instead of the real observations, in addition to the real observation, we are starting the observing the model spectrum of the model T galaxies using the model developed by Wada-san, so-called the radiation fountain model, in which we means if we have the torus and if you are just at the informed material, the torus cannot be thick as we could imagine. It should be quite flat. And if you are going to have the thick structure, you need some kind of the mechanism. So here we assume the radiation from the center and also this supernova feedback to make this structure. So this is a self-consistent model to make this torus-like structure. And we are using this model, we make a sort of we try to simulate our observation. And the first result is actually the dust continuum emission at 4.7 microns. And the really good news is actually the 80% of the dust thermal emission is dominated by the emission from the star. So our first assumption that at 4.7 microns, the continuum emission should be dominated by the emission, dust emission from the inner edge of the torus is valid. So the another point is if we could observe really observe the spectrum, including the systemic one and also outflow and inflow, and we seem to be able to reproduce. All the line ratio could be different from the real observations, but we do have the inflow component and also the outflow component as a function from the center of the star. So now we have these models so that we can change the parameters as you like, and also we can change the viewing angles so that we can constrain what is the really critical parameters to make this absorption observable or not, with the combination of the emission observation and also the absorption observations. So we believe that we have detected the hot several hundred Kelvin gas component with a large Coulomb density, larger than the 22. And actually the absorption observation is really complementary with the emission observations. And we have we believe that we have a hint of the structure of the molecular tora, inside of the molecular tora from this combination of the emission and absorption observations. And they would like to solve why we can observe this observation only toward some limited CFAT2 type galaxies and not every of them. So thank you very much.
Thank you very much for this nice talk. So we have 5 minutes for Q&A. So okay, I find a question in Slack. So let me go to Slack first. This question is from Professor Matt. When you detect CO absorption, is this always 100% correlated with detecting deep silicate absorption, or can they be different in some labs or ULABs or some other galaxies?
Oh, I can catch the point very well. But for the silicate, actually the silicate absorption feature and the CO absorption features they correlate pretty well. Whenever we detect the CO absorption, we do detect the silicate absorption, but not vice versa. Even with the galaxies with a very deep silicate absorption, we sometimes could not detect the CO absorption.
Okay, thank you very much. It should be very clear answer, I suppose. And then another question is from Thomas-san. Can the model or viewing angle explain the difference between MRK231 and NC253?
Well, it is not clear yet, but right now we assumed here the viewing angle is 75 degrees, and if it's completely edge on, actually the optical depth is too large, so we cannot detect this feature in absorption. So the viewing angle could be one of the key parameters which could affect this absorption detection. But the Markarian 231 is a bulk quasar. So at least in optical wavelengths, we should be seeing the outflow component probably at the surface of the molecular torus. So I'm not completely sure if only the viewing angle could solve this puzzle.
Okay, thank you very much. Any other questions from the topic? I have a question, Nakagawa-san.
Yep.
I think I don't know if this outflow is related to the HM feedback or not, but I think it's very interesting to estimate the mass outflow rate or something like that. And then my question is it possible to calculate the outflow rate from your absorption observations?
Well, in principle, we can make a guess. The problem is we have to assume the sort of the geometry to make the mass estimate. What we observe is only the m dot in one line of sight. So, yeah, so we made the estimate. I don't remember the number on top of my head, but under some assumptions, our result is consistent with the outflow component observed in ALMA, and so could be related, but we have huge uncertainty.
Thank you very much. Related to this question, you also detected the inflow motion of gas.
Yeah.
So does this inflow material is consistent with observed, say, Eddington ratio or something like that?
Again, actually the m dot depends on the assumption we have, but right now the mass flow rate derived this from this component E, which is the inflow component is something like a 0.1 solar mass per year. But this guy is a 10 to the 12 solar mass, 12 solar luminosity, which requires, roughly speaking, 1 solar mass per year.
Oh, okay.
So I'm afraid it's a little bit not enough, even with the 100% Eddington luminosity. It's not good enough.
Oh, okay. Maybe depends on carbon refraction or.
Yeah, could be. Yeah.
Okay, thank you very much for very clear answer. Okay, it's time to go to next speaker. So let's speak again.
Thank you.
Next speaker is Mr. Simon Ho from National Tsinghua University.